Hello everyone, this time we're going to cover AP Chemistry 2021 free response questions. In this time, we're going to work on number 1 of the problem. My best advice for you who are preparing for this upcoming AP Chemistry 2022 exam is that go over this last year's problem or the previous year's problems, especially when you're given a short period of time. Let's say we have only 1 month to prepare this exam, then it is most efficiently prepared. You can be prepared well when you go over the exam problems for the last years. Okay, let's go over number 1. Methanoic acid HCOOH ionizes according to the equation. Let's say we have solvent water. Remember that in general chemistry, we are only considering about aqueous solutions when we have solute, such as here, methanoic acid is dissolved in water. Then small percentage of methanoic acid, this is a weak acid, will be dissociated in water, producing hydronium ion and hydrogen, this conjugate base of methanoic acid, methanoate ion, and the equilibrium constant Ka is given as 1.8 times 10 to the negative 4th power. Remember that for a strong acid, Ka value is very large. 1 and 10, even larger than 10. That's Ka value. For a weak acid, Ka value is small, less than 1. Typically 10 to the negative 2, 10 to the negative 3, 10 to the negative 4, 5, 10 to the negative 7, so on and so forth. So let's think about the concept of weak acid. Here, we have a solute. This methanoic acid is dissolved in water. This is a weak acid. And because this is weak acid, the water is functioning as a base in this case. Water can be functioning as an acid or base depending upon the solute. And so then this weak acid will be giving out, donating hydrogen ion to water, forming hydronium ion and this methanoate ion. Number A, write the expression for the equilibrium constant Ka for the reaction. And equilibrium constant is the product concentration, molarity, and to the power of the each coefficient. Here, all the coefficient is 1. So then the product side, hydronium ion and methanoate ion, HCO negative concentration, the bracket indicates the molarity divided by the concentration of the methanoic acid at equilibrium. That's the expression. Here, note that the water does not appear in the expression. Water is a solvent. Solvent does not appear in that Ka expression. Note that one, please. We are only dealing with the solute, which is the methanoic acid in the product. Now, in this case, typically it's asking about the pH of the solution. We have 0.25 molarity of methanoic acid. Then calculate the pH. In this case, we need to set up ice table. What is the initial concentration? What is the change in concentration? And when the equilibrium is reached, what is the concentration at that time? So let's set it up. Let's write the equation. Methanoic acid and water. It is dissociating to generate hydronium ion and methanoate ion. Initially, we are given 0.25 molarity. Here, all the concentration, all the values are molarity. 0.25 molarity is given. And water, the amount of water is large. This is solvent. So we have much more like amount than the solute. And we are not considering the amount of water. So then we don't need to consider the amount of water. What about hydronium ion and methanoate ion? Methanoate ion initially 0 because we didn't add any methanoate initially. What about hydronium ion? We have a small amount of hydronium ion. We know that in neutral water, we have 1.0 times 10 to the negative 7, which is, very small amount. So because the amount is very small, we ignore the presence of hydronium ion initially and change. So a small portion of this methanoate ion, 0.25 molarity, will be dissociating. We don't know the amount, so let's set it up as X. So this one will be decreasing, it is minus X. And because it is one-to-one reaction, then hydronium ion and methanoate ion will be generated by X molarity. So when at equilibrium, initial 0.5 will be decreasing by X. So 0.5 minus X will be remaining, and the product will be X and X molarity. Now let's plug in the values at equilibrium to the expression of Ka. Then it is X times X squared divided by 0.25 minus X. And here we are given the value of Ka. So we have two options. First, work on plugging into the Ka and work on the quadratic equation. Or we have a second option, which is approximating that X is much smaller than 0.25. So 0.5 minus X is approximately equal to 0.5. This is a working in many cases. Okay, in this case also the Ka value is 10 to negative fourth power. So I think it is small enough and we can use approximation. Later we'll be checking if this approximation is a valid assumption. So let's solve it now. Ka expression is simplified to X squared divided by 0.25, and let's plug in the value. 1.8 times 10 to negative 4 is given. Let's multiply 0.25 on both sides, then X squared is equal to 0.25 times 1.8 times 10 to negative 4. Now let's take a square root on both sides. X is equal to square root of the value. When I plug in those values into the calculator, then I find out the value of X is 6.7 times 10 to the negative 3. So when the calculation is done, let's see if our assumption is valid. Let's calculate percent dissociation. So out of the initial amount of 0.25, how much is it dissociated? So X over the initial amount, initial concentration times 100, 6.7 times 10 to the negative 3 divided by initial concentration 0.25 molarity. It gives us 2.7%. Then our criteria is 5% rule. When the percent dissociation is less than 5%, then our assumption is valid. The dissociation value is small enough. Okay, so then our approximation is valid, so we can move on with this value. Approximation valid meaning, our approximated solution and our rigorous solution is close enough. Okay, we don't need to do rigorous calculation. We have a little bit of error range in measuring the pH, so it is accepted. The error is accepted in this case. Okay, let's move on. Hydronium ion concentration determined to be 6.7 times 10 to the negative 3. pH is simply taking negative log of the hydronium ion concentration. When I plug in those values into my calculator, it produces 2.17 as a value. Remember that. Let's think about the number of sig figs. When the hydronium ion is given 2 sig figs and it is leading up to the 2 decimal places, 2.17. Now let's see what is the meaning of 2.17. We know that at neutral water, neutral solution, the pH is 7.0, and the pH has a range from 0 to 14, usually in the range that we are interested in. And from 0 to 7, that's acidic region. And current pH is 2.17. When the value is like close to 0, 0, 1, 2, in that range, we call the solution strong acidic. When the pH is close to 7, pH 4, 5, 6, we said is weakly acidic. Currently 2.17 is close to the strong acidic solution. Why? Like, as I said, methanoic acid is a weak acid. Why this weak acid produces strong acidic, relatively speaking, strong acidic solution? Because the concentration is high, 0.25 molarity. Again, 250 millimolarity is relatively high concentration, and the Ka value 1.8 times 10 to the negative 4 is among the weak acid relatively high. In combination of these two effects, it produces a little bit high, little bit strongly acidic solution. Okay, now let's move on. In the box below, complete the Lewis electron dot diagram for this methanoic acid. So show all bonding and non-bonding valence electrons. And we need to first remind ourselves about the Lewis electron, Lewis atomic diagram, hydrogen it belongs to group 1A. Hydrogen has 1 valence electron, 1 dot. Carbon belongs to group 4A, 4 valence electrons. So we put single dot on all 4 sides of carbon. Oxygen has 6 valence electrons, group 6A. So it has 2 lone pairs and 2 unpaired electron. So when you show this one, and hydrogen, carbon, and oxygen, OH, each one, hydrogen should be satisfying the duet, 2 valence electrons. Carbon and oxygen should be satisfying the octet condition. And then carbon and oxygen should have a double bonding. And carbon and oxygen, hydrogen, that bonding should be a single bond. So when I use a dashed line for a single and double bond, single double bond, this is the structure on the right hand side. And here COOH is called a carboxylic acid, is one of the functional group. And a compound, a molecular compound that contains this carboxylic acid is always a weak acid. Let's see an example. I drew the structure of acetic acid, CH3COOH. The COOH functional group is, again, this is carboxylic acid. That's why acetic acid is another weak acid. We have many examples of carboxylic acid, very useful functional group in organic chemistry, general chemistry, organic chemistry, and biochemistry. Many of the biomolecules also have this carboxylic acid. So let's get familiar. I wrote the Ka value for acetic acid, 1.8 times 10 to the negative 5. This is a weaker acid. When you compare relative strength of this acidity, this is a weaker acid than the methanoic acid, about tenfold. Let's move on to D, in aqueous solution, another molecule, which is a weak base. NH2NH2 is called hydrazine. The name is hydrazine. Hydrazine reacts according to the equation. Hydrazine is a weak base. Hydrazine, the structure, nitrogen has a lone pair, each of them. So this is functioning as a Lewis base, taking hydrogen away from water. And let us remind ourselves again about what are the weak bases. Weak bases, most of them, they are nitrogen compound. So when the nitrogen is found in the structure, that is functioning as a weak base. And so water here is functioning as acid because the solute is weak base. Now water is either can be functioning as acid or a base, in this case functioning as acid, producing conjugate acid and hydroxide ion. Kb, the dissociation constant, equilibrium constant of this weak base is 1.3 times 10 to the negative 6. And here, let me remind you again about another like nitrogen containing compound, methylamine. Methylamine has methyl group, CH3, and NH2 group. The nitrogen has a lone pair. Methylamine is again another weak base. Now write the balanced net ion equation for the reaction that occurs between this hydrazine and the methanoic acid. Methanoic acid is a weak acid and hydrazine is weak base. So weak base is now accepting proton. The weak acid is donating proton. So then proton in the carboxylic acid group from the acid is offered, donated to the base. And so conjugate base is developing negative charge, and hydrogen ion is the proton is transferred to the base. Proton carries positive charge. So then it is a conjugate acid has positive charge. And a 50 milliliter sample of 0.5 molarity of this hydrazine reacts with 50 milliliter sample of 0.5 molarity of methanoic acid. And let's think about it. Weak acid, weak base, it reacts again, and their volume and molarity exactly the same. So when I calculate the mole number of each of the chemical species, the volume multiplied by the concentration, it gives me 12.5 millimoles of each of hydrazine and methanoic acid. When the value is different, it becomes complicated because both of them, they are weak acid and weak base. So it is not easy to calculation, but in this case, they are equimolar. Their concentration, their mole number is the same, so it's easier to calculation. Okay, so in this case, we can simply think about which one is stronger in its acidity or in its basicity. Let's think about Ka value and Kb value of each of the chemical species. Ka value, equilibrium dissociation constant of methanoic acid is 1.8 times 10 to negative 4, and this hydrogen is 1.3 times 10 to negative 6. In this case, we always focus on this exponent portion. Okay, the number is less significant. The exponent is more important. One is 10 to negative 4. The other one is 10 to negative 6. 10 to negative 4 is 100-fold larger than 10 to negative 6. So we see that Ka value of the methanoic acid is about 100 times larger than the Kb value of the hydrazine, because this is 100-fold larger, meaning that methanoic acid is stronger in its acidity than the basicity of the hydrazine. So the solution will be acidic when we are given same mole number of these two chemical species, because methanoic acid is stronger in its acidity and it will be functioning stronger. Now let's move on to the next problem. Now it is combining this problem with the gas problem, gas equation. When a catalyst is added to a solution that contains this methanoic acid, a reaction represented by the following equation occurs. Methanoic acid is now dissociated into to form gas molecules. A lot of gas will be bubbling out of the solution. First, hydrogen gas and carbon dioxide. Is the reaction a redox reaction, an oxidation reduction reaction? Justify your answer. Okay, and it will be helping us to, when you draw the Lewis structures, methanoic acid is carbon, hydrogen, carbon like this way, and then it is dissociated into hydrogen and carbon dioxide. Let's think about two methods. First method is more rigorous method. Let's assign oxidation states to the atoms and see if the oxidation number of the atoms are changing or not. For example, let's take a stepwise approach. Let's assign hydrogen +1 and oxygen -2. Remember, among the non-metals, hydrogen has the smallest electronegativity. So hydrogen is always a +1 in a molecular compound that contains non-metals. And oxygen is almost always -2. There are small exceptions, small number of exceptions, but almost all the cases, oxygen is always given oxygen number of -2. Why? Because oxygen has the highest electronegativity, second to the fluorine. So always assign +1 to hydrogen and -2 to the oxygen. And step 2, when we add up all the oxidation states, it becomes the sum of oxidation states become equal to the charge of the compound. For a neutral molecule, the charge is 0. Neutral molecule, as the name indicates, it is neutral. So then sum of all the oxidation states must be 0. Let's think about this methanoic acid. Methanoic acid contains 2 of the hydrogen, 1 carbon, and 2 oxygen atoms. When you add up all the oxidation states, it must be 0 because methanoic acid is neutral molecule. So 2 times 1, C, is unknown, and 2 times -2 must be 0. So 2 plus C minus 4 equals 0. C minus 2 equals 0. Let's add up 2 on both sides, and C equals +2. So we find out the oxidation states of carbon in the methanoic acid is +2. Let's think about carbon dioxide. Carbon dioxide, carbon plus 2 of the oxygen is 0. Carbon dioxide again is a neutral molecule. So carbon plus oxygen here in this compound is always -2. In a compound is -2. Remember, in an element it is 0, but in a compound, oxygen is almost always -2. Then carbon minus 4 equals 0. When you add up 4 on both sides, you find out that carbon, the oxidation state is +4. And remember, like many times in combustion reaction, many of the reactions, it produces carbon dioxide as a final product. And carbon dioxide is the most oxidized form. Let me write it here. CO2 is the most oxidized form. Most oxidized form of carbon. carbon can have oxidation number, oxidation state between -4 to 4. Carbon has 4 valence electrons. So when it loses all of them, it is +4. And when it gains 4 of them, it is -4. So then oxidation number of carbon is in between +4 and -4. And the most oxidized form is carbon dioxide. Okay, so then when we see many bioreactions, many combustion reactions, it is producing carbon dioxide, most oxidized form, and the reduction potential of carbon is released as heat. So that's why all the combustion reactions, they are highly exothermic reaction. Okay, now we are ready to look at the change in oxidation number for this reaction. So methanoic acid is decomposed to hydrogen and carbon dioxide. The carbon initially +2 and changed to +4. So it has lost the electron density around carbon is decreased. So this is oxidation. Oxidation is loss of electrons. Oxidation, and by the way, the hydrogen initially +1 in this compound, in the element it is 0, it is reduction. So oxidation reduction has occurred. Remember that oxidation and reduction reactions always occur in pairs. They cannot be separated. Oxidation cannot be occurring by itself. Reduction cannot be occurring by itself. They are always occurring in a pair. We call this one oxidation reduction reaction. In short, redox reaction. More simplified approach for this one is recognizing this fact and gaining of hydrogen. Hydrogen is least electronegative among all the non-metal elements. So gaining of hydrogen is reduction and loss of hydrogen atoms is oxidation. Let's look at the methanoic acid. Methanoic acid has in the structure 2 hydrogen, 2 oxygens, and 1 carbon, and it becomes carbon dioxide. And it is lost. 2 hydrogens lost, and carbon dioxide has 1 carbon and 2 of oxygen only. It is a loss of hydrogen atoms. This is definitely oxidation. So when you see the structure, loss of hydrogen is oxidation, or gaining of oxygen is oxidation. Gaining of oxygen, let me write it here. So gaining of oxygen or loss of hydrogen, they are the case of oxidation. In this case, loss of hydrogen occurs, and we know that it is oxidation. Then the other case is hydrogen must be going through a reduction, because oxidation reduction always occurs as a pair. And next problem is asking about the gas reactions. The reaction occurs in a rigid 4.3 liter vessel, a rigid wall, meaning the volume doesn't change at 25 degrees C at room temperature, and total pressure is monitored as shown in the graph. The vessel originally did not contain any gas. It didn't contain any gas. It is a vacuum. It is only the liquid. Calculate the number of moles of carbon dioxide gas produced in the reaction. Assume the amount of carbon dioxide gas dissolved in the solution is negligible. When carbon dioxide is produced, some of the content will be dissolved in the water, but that the amount is small, so let's ignore it. So total pressure is monitored as time is progressing, so reaction is progressed. And from the initially 0 atm, no gas is in the reaction vessel, but as the reaction progresses, it produces more and more. It was reached a equilibrium state. I mean, the reaction is complete, and the gas pressure is 24 atm. Remember the equation. This one, the methanoic acid is decomposed to produce hydrogen gas and carbon dioxide gas. I want to point out the state of the product. Both of them, they are gases. Remember, and also look at the stoichiometry. From decomposition of 1 mole of this methanoic acid produces 1 mole of hydrogen gas and 1 mole of carbon dioxide. So then the mole number of hydrogen gas and carbon dioxide must be equal, because it is 1-to-1 ratio. Then in the case of this kind of case, we are always thinking about when you are given gas phase reaction or gas is involved, always think about ideal gas law. Okay, so ideal gas law, write down ideal gas law, write the equation. PV equals nRT. This one is asking about the mole number. So then let's rearrange the equation. N is equal to PV over RT. Okay, here R is the gas constant, 0.08206 liter atm per mole K. So then the pressure of the equation must be in atm, atmospheric pressure, volume must be in liter, and temperature must be in Kelvin. So many times pressure is given in millimeter mercury, millimeter Hg, then we need to divide by 760 to turn into atm. Many times volume in the laboratory scale is given in milliliter. So we need to divide by 1000, then change into liter. Many times our thermometer has a unit of Celsius. So we have to add 273.15. Sometimes 273 is good enough to turn into a Kelvin unit. So let's check it out. The total pressure is, when the reaction is complete, 24 atm. Volume of the container is V is the volume of the container. Gas is expanding and fill up the whole container. So then V is the volume of the container is 4.3 liters. It is rigid, it doesn't change. Temperature 25 degrees C, let's add up. 273, then 298 Kelvin. We are ready. Now plug in those values into the equation. Number of moles from the ideal gas law is equal to PV over RT, 24 atm multiplied by 4.3 liters, divided by 0.08206 times 298 Kelvin. So now let's take care of the units. atm divided by atm, liter divided by liter, and Kelvin divided by Kelvin. This one all cancels out. We have 1 over mole, that is mole. And just calculate the number. 24 times 4.3 divided by 0.08206 and 298. So when I'm teaching students and I see the most frequent error they make, up to here, they are doing fine. But when they plug in these values into a calculator, they forget to put the parentheses. So let me point out here, parentheses is important. When you plug in those values, how you calculate is 24 times 4.3 divided by, you put parentheses open, and 0.08206 multiplied 298, you have to close the parentheses and enter. Then it'll be giving you 4.22 mole. Let's think about sig fix. 25 2 sig fix, 4.3 is 2 sig fix. Other numbers has more than 2 sig fix. Then our final answer, you should have 2 sig fix. The answer is 4.22. Let me underline the second sig fix 2. And this is not a final answer yet. So let me carry this one. And here it's asking about mole number of carbon dioxide. So let's think about it. So this is a total number. And I use total pressure. So the N must be a total mole number. And then let's think about what is happening in the structure. In that chemical reaction, it produces two different gases. One is hydrogen gas, the other one is carbon dioxide. And then they are equimolar because it is 1-to-1 ratio. Okay, so then total mole number, this is a mixture. Total mole number is equal to the mole number of each gases. Mole number of hydrogen gas, mole number of carbon dioxide gas. Because it is 1-to-1, the mole number is the same. So then we can just set this one as 2 of mole number of carbon dioxide. So I consider this one and substituted this one to the hydrogen. Hydrogen is equal to mole number of carbon dioxide. So, and then let's divide by potential by half, 2, and then mole number of carbon dioxide is half of the total mole number. 4.22 divided by 2 is 2.11 mole. Finally, let's think about sig fix. We need to represent final answer with 2 sig fix. So let's drop 1 here. Final answer is 2.1 mole. That will be the final answer. Okay, now we have come to the last problem. After the reaction has proceeded for several minutes, does the amount of catalyst increase, decrease, or remain the same? Justify your answer. Let's think about it. Okay, catalyst is a very important concept in chemistry. Catalyst makes the reaction go faster, and without catalyst, many reactions are practically not useful for us, for our purposes. And last year, in 2021, the Nobel Prize in Chemistry went to the catalyst, organic catalyst, chemist who has studied about organic catalyst. So concept of catalyst is very important. And let's think about the function of catalyst. catalyst makes the reaction occur faster. It is involved in chemical reaction, but it is regenerated. When the reaction is completed, it is regenerated at the end. So the amount of the catalyst doesn't consumed, is not consumed in the chemical reaction, and amount is remains the same. That's the concept of catalyst. Okay, everyone, so let's sum it up. This problem is asking about the acid-base questions, and acid-base equilibrium is most important concept, like one of the most important student learning outcome in general chemistry and AP chemistry. So the concept of it is leading up to the concept of a buffer. Buffer is the most important concept in biology, biochemistry and biology. All of them, they're using buffer. In order to understand buffer, we need to understand the weak acid and weak base and its conjugate based equations. So this problem is asking us those concepts, and also it is making a connection with the catalyst and also the gas reaction. So it is asking us a multidimensional. This one is trying to gauge students' understanding about multidimensional perspectives from these acid-base reactions. And thank you, everyone. So hope this one helping you in preparation for the upcoming AP exam.